Okay, hope am I audible? So let's split my screen. Okay, so today we'll discuss basically the data analysis in Mathematica, so estimate of error and the curve fitting. So in these tutorials we will discuss the statistical versus systematic errors, okay, and propagate errors analytically and numerically as well. So work with just a minute, yeah. So work with real and simulated dataset in Mathematica and perform linear and non-linear curve fitting and extract parameter uncertainties, okay, and correlations. And then we access goodness of fit and residuals. Okay. So let's first start one by one. So first start with a very basic thing. So the type of errors. Okay. So every experimental or numerical measurements carries some uncertainty, right? So keep in mind that the error and uncertainties are two different things in scientific data analysis, right? So usually when we are talking about the error in the experiments, okay, we are always talking about uncertainties. Okay. So what is the difference between these two? So an error is the difference between a measured value and the true value. So we can define in this way. So let's E equals to your error is equals to x measure. So this is the measure value and this is the true value. Okay. So the difference is the error. Okay. Since we do not know the true value is, okay, so we do not know actual what is the error is. Okay. So what do we do? So the quantity is uncertainty. So they are the quantitative estimates of how large those deviations might be. So let's say I have a x. So this is the measure and x naught, okay, is my is my true value, okay, and then we are basically within plus minus sigma x. So this is the uncertainty. So your measure value, let's say your true value within 1 sigma or 2 sigma, okay, within some uncertainties your true value is, okay, right. So an uncertainty is an estimates of the possible size of the error in a measurement, right. So the uncertainty is a things we are always talking about. So when we are talking about error, we means the uncertainty. So, okay, so this thing is clear or not, okay, because so the error and uncertainty are two different things, okay. So you should keep in mind, okay, those things, those differences. So since we do not know the true value is, okay, what is the true values for some observables, okay, so we do not know what is the error is, right. So whatever you measure, since we do not know the true value, so how do you calculate the error, right. So you always predict this, okay, that how large the deviations from the true value, okay, within some probability, right, that is the uncertainty. So let us say within 1 sigma or 68% probability or 95% probability. So I have measured, let us say this x, okay, and my true value is x naught, okay, and I can say only that, okay, so my measured value the true value is within 5%, so within 1 sigma or 2 sigma, okay, within 95% probability, okay, my measured value are belongs to, okay. So this is the way we are always talking about uncertainties, okay. And there are two type of uncertainties. One is the statistical uncertainty. So this is the uncertainty that estimates, okay, a random basically errors due to finite data, okay, because we have some finite data sets, okay, and that is the statistical things, because if you considering the limited data, okay, and there are some random errors coming from this. So this is the statistical uncertainty, okay. And the other type of uncertainty is the systematic uncertainty that estimates the possible biases in measurements or modeling, okay. So that is from the system, because if you model, how do you model this data set in a mathematical models. So because of this there is a uncertainty and also in some biasness in your measurements, okay. So these are called the systematic uncertainties, okay. So these two types of uncertainties, okay. So here I will discuss only the statistical things, because systematics is not our controls, okay. So in data analysis we are always when we are talking about error bar, so this basically represent uncertainties. Okay, wait a minute. So I think okay, so okay, all right. So then I split my screen again. Yeah, so in data analysis, we always when we are talking about error bars, so that basically represent uncertainty, right? And the error propagation means the uncertainty propagations. Okay, and yeah, so and the fit error means the parameter uncertainties. Okay, so let's do the calculations in Mathematica. Okay, so calculate the error and things. So let's say I have a data set where I have only 5 data. One is 10.1 and 9.9 and 10.3 and 10 and then 9.8. Okay, so I choose this data set. Now I calculate the mean of this data, variance and the standard deviations. Okay, so these are the functions. Okay, inbuilt in Mathematica. So this is calculate mean. How to calculate means? Basically sum over this data and divided by the number of data. Okay. So in this way you can calculate the mean and then the variance. I calculate this one by one. So let's first calculate this mean, variance and the standard deviations from the inbuilt object that is already defined in Mathematica. Okay. So if you do this, so your mean is 10 to the 10.02 and then your variance is 0.037 and the standard deviation is this. Okay. So you can check this. So just calculate the sum of this. So basically, so how to calculate this mean? So this mean basically equals to the sum of the data plus okay, wait, I think okay, just a minute. Yeah, okay, so let's split my screen again. Yeah, right. So basically yeah, so we calculate first mean, and so this is the inbuilt functions in Mathematica you can use to calculate this. But if you explicitly calculate the mean, so how to calculate? You just sum the data set, okay, and then divided by how many data? 1, 2, 3, 4, 5. So divided by 5. So this 10.02, right. Similarly, you can calculate the variance and the standard deviations. Okay. Now we come to this point. There are difference between the standard deviations in Mathematica and how do you calculate. Okay. So I'll come to these points in a minute. Okay. So we can compare the theoretical definitions of the standard deviations with an inbuilt object in the Mathematica. So how do we calculate standard deviations? So first we calculate the mean of data, just the way we calculate here. So you can use also these functions mean data. Okay. So I calculate the mean value and I calculate the mean square value. So that means, so this is the a data set, right. So it's an array, right, one dimensional array. When we put a square, that means every element in this array is square. Okay. So just check this. So this is a data. So you just put a data. So you see, so this is an array and this actually this data set. Okay. So now when we call data square, right. So your data and then square. So that means every element is square. Okay, in this array. So you check. So the first element is 10.1, it's square. Okay, 102.01, and then 9.9 is square, right. So if you put a cube, so every element is cubed. Okay. So this is the things. Okay. So you can use this. So or if you multiply it with let us say 2, so every element is multiplied with 2, okay, in this array. So, this is basically multiplied. So, so now we calculate here. So, the mean of data. So, that means this. So, we already obtained this 10.02, and then we calculate the mean of data square. So, that means the square of this. Okay. So, I can calculate this. Okay. So, the mean values of this. Okay. And then you can calculate the standard deviation. So, this is basically square root of mean square minus mean value square, right. So, this is your mean value square, and then this is square of means. Okay. So, this is square of means, and this is mean and then square, okay. And their difference is the basically your standard deviation square. So, I just put square root. Okay. I hope it is clear. So, you see that this is 10.02 as already obtained, and then you can calculate the mean of data square by just putting this number. So, mean square plus, and then this is plus, this plus, right, and divided by, we have a 5 data set. So, divide it over 5. So, you see 100.43, right. So, this is the value we just obtained. Okay. So, the mean is actually correctly calculated, and then we calculate the manual HT. Okay. So, basically standard deviations by using this formula. Okay. So, you see that 0.17247, but here we obtain 0.192345 when we calculate the standard deviations. Okay. You see the difference, right. So, you just choose this. So, your standard deviations you see, right. So, you calculate by using this formula this, but here is basically 0.19235. So, what is the fallacy here, right. So, the difference arises in the denominator used in the calculations, right. So, when we calculate the standard deviation, right. So, when you calculate the standard deviations by this formula, right. So, how to calculate the standard deviations? Using this formula, x square minus x average and whole square divided over n, right, because I already divided by 5 and this is divided by, when we calculate mean we divided by 5, right, and when you calculate data square and then mean, okay, the square of the data and then we calculate the mean. So, this is basically x square over n. So, this, but in Mathematica they use n minus 1, right. So, this is not n, but they use n minus 1. Okay. That is why when you calculate the standard deviations using these functions, okay, you will get some bigger number than this, okay, because your numerator is smaller. Okay. So, I will cross check. So, let us say, so your standard deviations then, so they use n minus 1. So, I multiplied with n minus 1 over n. Okay. I think some people might be joining. Okay, sorry for this. I think I have to. Yeah, okay, I think. Okay, anyway, so let's split my screen again. Yeah, so let's split my screen again. Yeah, so so you see that so the difference is, so now if we multiply it with this, the square root of n minus 1 divided by square root of n, such that we get the theory results. Okay, how to calculate this way, right. So, we just multiplied n minus 1 over n. So, you just quick check this, you see that 0.17 to 0.47. Okay. This is the value we obtained by this definition. So, right. So, now we match. Okay. So, this is the quick way check. Okay. So, that means your standard deviations in the Mathematica, they use n minus 1, okay, instead of n. Okay. So, this point is clear or not? Okay. So, I think this is clear. So, this is the difference. So, that is why when we calculate the standard deviations, do not use these functions. Okay. We just use this. Okay. If we use n, okay, in the denominators. Okay. I will tell you in a minute. Okay, what is the difference between these two? Okay, why when we consider n minus 1 and when we consider n, okay, in the denominator. So, when doing curve fitting or error analysis, always use n minus 1 in the denominator, right. So, if you calculate error analysis for a data set, okay, in your experiments, okay, then you use n minus 1 in the denominator. Why? Because because your measurements is a typically refer the theoretical description of a complete data set. Okay. So, if you calculate theoretically, then you use n. Okay. So, this Bessel corrections is n minus 1 in the denominators actually impacts how we evaluate the quality of a fit, and specifically when we calculating the reduced chi-square statistics. Okay. I will come to this point when we calculate this reduced chi-square. So, the one thing is clear here, that when we use n, that means it is basically populated, okay, and when we use sample, that is basically unit experiments. Okay. So, you have some sample data. Okay. So, then you use n minus 1 in the denominators. Okay. Okay. So, while doing you curve fittings or error analysis, you always use n minus 1. Okay. So, that is already encoded in the standard deviations, these functions in the Mathematica. Okay. So, this is the crucials, but if you calculate some theoretical values, okay, so then you use n. Okay. So, that means you have to multiply it with this factor, okay, in order to get a correct result. So, big crucial these two differences, okay, when you are appearing in some quiz or exams. Okay. So, for sample data set or this measurement of real experiments, you always use n minus 1. So, these Bessel corrections are important because they actually impacts how we evaluate the quality of fit. Okay. So, when we perform a chi-square analysis, okay, I will come to this. Okay. And then we can also calculate the standard error of the mean. So, how to calculate the standard error? First, we know the standard deviation sigma and then square root of n. So, this is basically total number of data. Okay. So, this is the standard deviation. So, I use again the Mathematica inbuilt functions. Okay. So, if you calculate theoretically, you just multiply this. Okay. So, this is the standard deviations, and then I calculate the standard error of this. So, I divided by square root of length. So, length is basically ln is basically the length of the data set. Okay. So, you can quickly this. So, this is your error of this. Okay, of your standard deviation. Sorry. So, now you can easily cross check this. Okay. So, let us say I consider different sample size. One is, so this is my sample size is how large, I just check this. So, here my sample size is basically 5, right, because length of data is 5. So, I have a 5 data sets, 5 data in the data set. So, I consider a sample size 5, 20 and 100. Okay. So, that means my first data set contains 5 data and the second data set contains 20 data and third data set contains 100 data, right. And I plot basically the mean of this data set. Okay. So, I consider all this the normal distribution. So, this is basically Gaussian distributions. So, this normal distributions means the Gaussian distributions with a 0 mean and 1 standard deviations. Okay. Okay. And this n is basically your variables, that is thousands and -1 to 1 with a step of 0.05. Okay. And I calculate the mean. Okay. So, if we see this, where n is basically the sample size. So, this is 5, 20 and 100. Okay. For 3 values I plot this. Okay. So, this is the grid plot. Okay. Because we have a 3 plot for this 3 sample size. So, I have to create a grid of these plots. Okay. Just use this. Okay. So, you see that in case of 5 data sets. Okay. So, let us zoom in this thing. Yeah. So, in case of 5, when the data set number of data is 5. So, we have a 0 mean and the standard deviations 1, you see. So, the standard deviations is large. Okay. So, if we increase the data set, okay, if we increase the number of data, let us say 20, n equals to. So, then you see the sharp Gaussians. Okay. And again if you increase n equals to 100, then again sharp. Okay. So, your error is basically small. So, that is why I calculate how to calculate the standard error of the mean. Okay. So, this is basically you divided by square root of length of the data. So, if we increase the length of the data, so that means your this width is small, right. So, this width is small, the standard error of the mean, right. So, you see. So, this is basically actually the visual proof of central limit theorem, right. So, how the uncertainty in your measurements shrink to a value we increase the number of samples. Okay. So, let us say if you increase 100 to 1000, okay, then you will see. So, actually sharp Gaussians. Okay. I mean you have to increase the bin size as well. Okay. So, you see. So, I increase the bin, I reducing the bin size. So, you see that the sharp Gaussians. Okay. Yeah, this is fine, right. So, if you increase more samples, okay, then your error is small. Okay. So, that is the central limit theorem. So, that uncertainty in your measurements, okay, shrink as you increase the number of samples. Okay. So, this is the things. Okay. If you have any questions, you can ask, please. Okay. So, this is the visual proofs, and now I generate some pseudo data and visualizing this. Okay. So, let us we start by generating a sample of let us say 100 measurements for a physical quantity. Let us say I measure the length of a rod, okay, and with a known mean and the standard deviations, right. So, first I generate this data set from these distributions. Okay. So, this is a sample data, and I with a mean of 10.5 and the standard deviation is 0.2 sigma. Okay. And I generate 100 data sets from this Gaussian shaped things, right. And this is a random thing, okay, because random variate I randomly generate data from this, okay, from this distributions. Okay. And then I plot this. Okay. So, this is basically histogram of this data set, okay, and then some chart style and label, you know very well these things, okay, how to plot. So, you see. So, this is the bin size. Okay. So, for I have a mean is 10.5. So, you see that around 10.5 I choose a random data set and make a histogram plot of this. Okay. Now, I calculate mean and the standard deviations and the error, okay, standard deviations by square root of n. Okay. So, this is the length of data. Okay. So, we calculate this. So, you see your mean is 10.4809. Okay. So, now you see, so you start with some distributions that is 10.5 and with a mean 10.5 and standard deviation 0.2, but you are often different things from this. Okay. Once we generate the data set and then we make a histograms and then you calculate the means. Okay. So, you see that we are getting different things. Okay. 10.48, this is not 10.5, and your standard deviation is 0.2. You generated from this sample randomly. Okay. But you are often but you are getting 0.2363, okay. And your standard deviations is basically square root of n. So, divided by 10. So, because we have 100 data sets. So, if we divide it by square root of n, so that means it is basically divided over 10. Okay. So, it is exactly this. Okay. So, 0.23, okay. 023, right. So, if you divide it by 10 this, so you get this. So, if we now plot this, okay. So this is the plot, that is the normal distributions, again the Gaussian with a 0 mean, and one is the one is the standard deviations, and if we plot this. Okay. So, this is the PDF. So, this is basically your Gaussians, okay, with a 0 mean. So, that means there is a no x minus, so basically x minus x average, right, and then whole square, right. Since the x average is 0 mean, so there is a only x variable, and the standard deviations there is a no sigma in the denominator, right. So, in generally there is a 2 pi sigma. So, you see that so in the all cases when we call these normal distributions, this means we are basically calling this, okay, with it. So, let us say I have a 1 mean and 2 standard deviations. So, you see, so this is basically square root of 2 pi, okay, because here 2 pi sigma square, okay, and then your x minus your mean is 1. So, x minus 1, okay, whole square over 2 pi, there is a sigma also. So, you can create 0 and then 1. So, your basically this is the shape, okay. So, when you generate the random data from these distributions, so that means you are generating number from these distributions actually, okay. So, this is the visualization. Now, we can random variate. So, I can generate the data, random data from this. So, you see that, you see. So, I will make a histogram plot. So, that is why. So, this is bin wise they can generate. Okay. If you just remove this, so this is the data set. Okay. You can also always you see that. So, you can always to visualize, you can make a histograms, that is the bin wise things. Okay. So, you can randomly generate. Okay. You can make running this different things. Okay. Again run, again different. So, this is randomly generate. Okay. The 1000 data, okay, from these distributions. Okay. So, basically your distributions is 10 and 0.2, and you have to call this is basically minus 22. No, I think this is too large. So, minus 12 to plus 12. No, your mean is 10. So, you can plot 0.9 to 9 to 11, that is fine. So, you see. So, actually you generate some random data from this. So, you can compare, right. So, this is basically 10.5 and here the 10.5 is there, right. So, you cannot cross this, okay. So, this is your boundary. So, this red line you have to always generate the data within that, okay. You can cross check, okay. So, this is the 9.5 and this, you can merge this and then cross check. So, always so this is the distributions and you can generate the data. So, now how to calculate the error bar thing. So, let us say I generate the data, okay, from this data set, okay, 0 mean and 2 standard deviations, okay, and my data set is 2I plus 5. Okay. So, this is basically some straight line, okay, and I is goes for 1 to 20 with a step of 1. Right. So, can you tell me what is the plot looks like? Can anyone tell me? So, let us do one by one. So, first, so this is the data set. Okay. Can you tell me when we plot this data, okay, how it looks? Okay. So, it almost straight lines, right, because this is my actually functions, right. Let us say 2x plus 5, okay, y equals to 2x plus 5, okay, and this x I have a 1 to some discrete points. Okay. So, 1 to 20 with a step of 1. So, this is basically your 1 to 20, okay, points with a step of 1. That means, I have a 20 points, but I add some random numbers to that points. Okay. So, that means, it's all points are, it is not along the straight line, but there are some fluctuations. Okay. So, we will see. So, if you zoom this, so you can see, okay, what do you see? So, you see that the data with errors, right. So, I plot the data with errors. Okay. So, that means for each point, let us say I, okay, this is my true functions, okay, and the error, right. So, you see that this point there is a no error, very small error, but this point there is a large error. So, that means, in this case when you generate this random variate distributions is basically large. Again for this point, again you are getting large error, and again the next point you are getting a small error. So, now if we just plot the data, okay. So, let us plot this data. Okay. Sorry, I have to put a variable. So, yeah, so I have a table. So, that is 1 to 20. No, this is a bad way to plot. Okay, so let us do this. Yeah, make a list line plot, that is good. So, list line plot, yeah, you see. So, your basically this is connected, you can also plot a scatter plot, I think it works. No, so in this case yeah, so you see that your first point and the second point and third point, so this is basically zigzag. Okay, now you can check with this. So, 1 to 20 at each points, okay, they can generate some random numbers, okay, because this 2x plus 5 is not actually holds, right, because we add some random numbers to that. Okay. So, this is the line. So, that is basically your 2x plus 5 lines, okay, you can check. So, this is your 5 and yeah, so they hit actually 5, right. So, this is 10 and this is 0. So, intersect at 5. Okay. So, this is the 5 and now I add a random number. So, that is why this is zigzag things. Okay. And you can, so here I plot basically the error, okay, at each point what is the errors. Okay. So, you can see there is a no error and then there is a error because this is deviate from this. Okay. So, let us say okay, let us say I have to assign some other things, data with errors. So, I just plot this. So, you see, so this is your 2x plus 5 line, and this is the points, okay, you generate randomly, okay, because you add this, okay. So, this is random things, okay. And here, so in this plot I plot this is basically around. So, I will come to this point, I am not discussing yet what is the around mean. So, around basically calculate the error, okay, for each points, okay. So, you see for this point the error is small, and then this point is error is large, again at point 3 again error is large, and then you can calculate this, okay. Okay, I generate this again. So, this is a random, that is why it's basically fluctuates. So, let us I generate this and then I can put this. So, you see that the first point is error is large, because you are predicted this and you are getting this value. So, the red one is basically the first one, okay. So, this is the data and this is 2x plus 5, okay. And I calculate the error around this point 2x plus 5 and then the error, okay. So, you see, and the second point is again small, okay. So, this is basically at 2 and this is 3. So, at point 3 again if you calculate the errors. So, you can in this way you can cross check that at 15 around the error is large. So, here we also that around 15 error is large, okay. And then is small, but here is large. So, okay. So, any questions so far? So, this is the error at each point, okay. So, this is your true value and this is the error, okay. So, you can use around functions, maybe I will come, I discuss not yet, I think in the previous class I discussed the around functions, right. Yes, I think previous class I discussed the around functions. So, this basically tells you what is the difference, how to calculate the error for each parameter values, okay. Okay, so next I will discuss symbolic error propagations. So, we will use Mathematica's symbolic engine to calculate how error in inputs affected your calculated result. So, we have some input variables, okay, and the error in inputs, okay, how affected your calculated results, okay. So, let us say I have a functions f, okay, capital F, a functions of x1, x2 and dot dot dot, okay. And I have to calculate the uncertainty of a functions, okay, and is determined by the partial derivative of the functions with respect to each variables and weighted by their individual uncertainties, okay. So, here x1 and x2 are the inputs, okay, and I know the individual uncertainties of these inputs. So, that is basically sigma x1 and sigma x2 and blah blah blah, right. And I have to calculate the uncertainties of the functions f, okay. This is things I calculate, okay, okay, from this, okay, and I know the error of the inputs, okay, x1, x2. So, the general formula is that, so this is your sigma f, so it should be capital F, okay. So, it is basically this will be capital F. So, the error of the functions f you can calculate in this way, that sum over I delta f over delta xi each variables. You can first you calculate the derivative of this partial derivative and multiply with the error of individual xi, okay, sigma xi, and then whole square. So, this is the formula, okay. And note that this is the uncorrelated, okay. So, these x1 and x2 are not correlated, okay. If they correlated, then this formula change, okay. I will come to this point, okay. First I will discuss uncorrelated variables x1 and x2. So, let us say I have functions f of xy. So, that is basically product, okay, x times y. Okay. So, I first calculate the derivative with respect to x and derivative with respect to y, because I have a two variable x y, okay. So, let us say x1 equals to x and x2 equals to y. So, then if you calculate this, the first derivative with respect to x, can you tell me what is that? It is y, right, because if you derivative with respect to x, okay. So, the remaining one is y. If we derivative with respect to y, then it is x, right. So, now I calculate the sigma f. So, this is basically this, and the square root of first one, the d. So, this one d f of x. So, you see d f of x times the standard deviations of x. So, this is I call s x, okay, small x and small x, okay. So, this is basically sigma x, okay, first variable, and the second variable is y. So, and then whole square, right, and this, and then the sum over. So, this is basically sum over I, and for second variable I have a d f of x y comma y with respect to y, because my x2 is y, okay. And then the standard deviations of this is basically s y. So, and then whole square, right. So, we calculate this. So, this is basically a result. So, x square over x square times s y square plus s x square times y square, okay. So, this is the general result, okay, formula for two variables. If this is a product x y, and then this, you can use this symbolically, okay. So, all things are the symbolic calculations. Now, if you calculate, so you can also define a more general function. So, this is basically I define this function. So, is a propagate error function, first variable, second the variables, okay, VARS means the variable list, okay, and then the sigma list, okay, the standard deviation list, okay. So, I define this. So, this is basically square root again the total. So, that means sum over of. So, total means the sum over, okay. So, this sum over, and then the d I first. So, this is my functions, okay, whatever the functions is. So, I put the functions here, and so this is the first argument of this variable list, okay, and this is the second argument, okay, of variable list, okay. And then we can calculate the transpose of variations and the sigmas, okay. So, in this way I define the propagate error, okay. So, this is basically same. Now, if we calculate, let us say I have a x y, the same functions x y. So, I put in place of functions, and my variable list are x y, my variables are x and y. So, I put the second case my variables x y, and third case I put sigma list, okay. So, what is the values of sigma? No, I denote s x and s y. So, I assign here s x and s y, okay. So, now we calculate this. So, you see exactly the same results, okay. So, you can calculate, let us say I have a 3 variable x, y, z, let us say. So, this is very general, okay. Okay, let us copy this and then yeah. So, let us say I have a 3 variable. So, I have a functions that is f equals to x y z, okay, and I have a variable 3 x y z, and my standard deviation list are s x, s y and s z. Okay. Up to this point is clear. So, then you can calculate the error. So, you see. So, this is thing, okay. You can calculate using this formula, okay, and cross check this. Okay. So, this is your exercise. So, your functions now f of x y z, and then you first calculate with respect to derivative with respect to x, and then you calculate derivative with respect to y, and then you calculate derivative with respect to z, okay, and you just multiply this. Okay. So, you see you are getting these things. Okay. So, in this way, let us say I have a, so another example. So, let us say I have these variables. So, this is clear, means that if we define previously m r is, okay, sigma m, sigma r and sigma h, if we define previously, so that will clear things. Okay. So, that means I clear all the variables if I define previously. Suppose if we define previously here, let us say m equals to let us say x y z. Okay. So, here you define m equals to x y z. Okay. So, this m is defined unless you clear. Okay. So, in whole Mathematica notebooks, okay, in this kernel, okay, this m is equals to x y z. Okay. If you call this m, you see x y z. So, x y z actually assigned to m, okay, unless you clear these things. Okay. So, if you clear m, let us say I clear, so here you see, so here I clear m, right. Once you clear this, okay, so there is no longer m equals to x y z. Okay. So, now if you call this, okay, so this is a m. Okay. So, this is actually clear. Okay. So, that is why if you do some large notebooks, okay, and if you do not know what is the assigned to what variables, you just use whenever you use the variable, you first clear those variables. Okay. So, that is the best way you can do. So, I clear all these variables because I am now working with these variables later on. Okay. So, that is why. So, now I define rho equals to my m equals to, so this is the pi and r square h. Okay. So, this is the formula of a density. Okay. So, I rho equals to density. So, this is basically mass over volume. Okay. So, I calculate the propagate error of rho, okay, because you see, so this is basically your function is basically f. Okay. So, rho, here my functions is this, okay, and I calculate. So, I have how many variables? Can you tell me how many variables I have? So, it is 3 variables, right, m, r and h, pi is a number, right. So, I have 3 variables, and what is the standard deviations? The sigma m, sigma r, sigma h. Okay. So, we calculate the error, you see. So, Mathematica easily calculate the error. Okay. I mean using this formula. So, all these calculations are symbolically. Okay. And I see that I define the propagate error here, right. So, you have to define the functions. Okay. So, this is my function, so this is the formula. Okay. I define the functions here, okay, for any functions, any variable, any sigma. Okay. And also the number of things. Okay. How many number of variables you choose, it does not matter. Okay. This is basically in general. Okay. So, here I use this complicated function, and I use 3 variables because here 3 variables are there and the corresponding sigmas. Okay. So, once you provide this, you can calculate the error. Okay. Symbolically. Okay. So, now what is the implications of this? So, let us do numerically. Okay. Yeah, so far any question? Okay, let us do numerically. So, let us say you are measuring some kinetic energy of an object. Okay. Your formula is kinetic energy equals to half mv square. So, you have the mass m and the velocity v, both with known uncertainty sigma m sigma v. So, we have a two variable here m and v, right. So, this is the mass and v is the velocity, right, and you know also the uncertainty of sigma m and sigma v. So, those are the inputs, right. So, here you see the sigma m, sigma r, sigma h, those are the inputs. So, this is also known. Okay. So, your formula is the half m v square, and the error I already defined this propagate error. So, I now use these functions again. So, my functions is kinetic energy half m v square, and I have a two variables and also the uncertainties are sigma m sigma v, right, for these two variables. Okay. So, if we do this, so your result is basically symbolic things. Okay. So, these are the symbolic results. Okay. Now, I assign the values. Okay. So, if a value, so this is my lab values. Okay. I have a m is 0.5 kg and v is the velocity is 12.4 in SI units. So, let us say meter per seconds. Okay. And the standard deviations of m is 0.01 and standard deviations of v is 0.2. Okay. I assign those values. Okay. Now, I calculate the kinetic energy. Okay. So, this way you can calculate. So, this is the kinetic energy expressions, okay, functions, and I calculate the at lab values. So, I already assign my lab values, okay, to these variables m, v, sigma m, sigma v. So, we just put this symbol slash dot and the lab values. Okay. So, I will tell you. So, let us say I first calculate the kinetic energy, let us say k. Okay. I already assigned this k equals to half m v square. Okay. So, I calculate is this value, let us say m tends to 0.2, v tends to 1.0, okay, because I have a two variable m v. So, I just need these two. Okay. If you put any other variable here, they are not considered here, okay, because we only need two. So, we just put this t and you put this sign slash dot. Okay. So, they basically they compute the values of these functions when the m is 0.2 and v is 0.1. Okay. So, you see this is 0.1, you can cross check. Okay. So, if you put other number, let us say 0.5 and 12.4. Okay. So, it is 38.44 your values of the kinetic energy, okay, right, for this particular values of m and v. Now, I can also print this. So, this is my calculate kinetic energies, okay, equals to this value at this lab values. Okay. So, that means I will get 38.44, right. You see your calculated kinetic energy 38.44 and I put joule here, my unit SI unit, and the uncertainty, how to calculate the uncertainty. So, this is the k error I calculate already, the propagate error, okay, at the lab values. Okay. So, you will just put here, sorry, you will just put here the lab values. Okay. So, this is your lab values. Okay. I put sigma m, sigma v this. So, sigma m is 0.01 and sigma v is 0.2. So, once you put, so that means basically we assign whole things here, okay, whole things here. So, you see that 1.45889 joule. Okay. Actually, this is the results, right. Okay, here I use around things. Okay. So, you see again So, in modern Mathematica, okay, so basically if your Mathematica versions after 12, okay, so this is the versions of the Mathematica. So, I am using 13 Mathematica versions 13, okay, so this is after 12. So, the built in around object basically encapsulates a value and its uncertainty, okay. So, Mathematica will automatically handle the error propagations using the first order Taylor series expansions, okay. So, this is the thing. So, let us say I have to calculate the error. So, this is the around function. So, x 1 and then sigma x 1. Okay. So, your first variable x 1. So, this is basically 0.50 m, right. So, this is my first variable, right. So, I put here, okay, and sigma x 1 is basically the error associated with m. This is sigma m, right. I put 0.01. So, that is my m measure, okay. And v measure again, so it is 12.4, my second variable x 2, and sigma v is 0.2, right. Okay. So, now you see, just call this, okay, what is actually assigned to, okay. Let us say remove these things, then it actually show, okay, what is the values of these things. So, you see, so you are 0.5 plus minus 0.01. So, this is basically encoded in this format, okay, in the functions around. So, when you use around, so that means it is basically put a traditional form like x plus minus your error sigma x. So, this is the way I can also assign these things. So, these things I assign basically using around functions. Similarly, v measure I assign using around functions again. So, this is my results. Now, I calculate Ke final. So, that means your x m measure is basically this m plus minus this, and v measure is basically this plus minus this. So, if you calculate this, so you see 38.4 plus minus 1.5. So, I rounding off, okay. So, they rounding off, use some rounding rule. So, in this case the 38.4. So, the second digit is 4. So, it is basically less than 5. So, 4, right, 38.4 up to first digits, up to third significant digit, and your error is basically 0.5, 1.5. So, you see that 1.45899. So, you can, if you use significant digit things, okay, so it is basically 1.5. So, since I am use only one digit after decimal points, so that is why I also use one digit after decimal points in error, okay, right. So, now you see how what is the around functions, okay, and how it's actually calculate these things very quickly. So, here I use this formula, okay, to calculate this thing uncertainties, okay. But if you use around functions, okay, to assign the variables to, yeah, so to assign the value and the errors, okay, in a combined form using these functions, around functions, okay. So, then you can just calculate this by multiplying these two numbers with errors, okay. So, they use some first order Taylor series expansions, okay. You can calculate this. Okay. Yeah, any question? So, now if you go back to this thing, okay. So, here when you calculate these around things, okay. So, you see this is your 2i plus 5, okay, and this is some random real number, okay, 1. Okay. What is random real 1? You just put this here. see some random number, right. So, this is basically I plot that how do you plot error bar, okay, in a scientific plot. So that is why I just put some random numbers, okay, for each points I just put some random numbers. So random numbers, so that is my error, okay. So at the order 1, okay. So that is why all the numbers must be below 1. So it is 0 point something, okay. Okay, so that is why if you see, so this is actually some random errors, okay. So this is I am just showing that how do you plot with error bars, okay. So if you have some definite error, then you just remove this, okay. So let us say if you put 0.5, okay. So each data point have a error with 0.5, okay. Each data point, okay, if you plot along the straight lines have 0.5 things. So here so previously I compared these things, but you cannot compare because both are randoms, okay. So here when I assign some random real one, so they are basically randomly assign the error to each data point. So two randomness is there, okay. So when I plot this, so this is the red one, okay. So this is again random things, okay. I assign the random things and again I assign the random things, but these two random numbers are different, so they cannot be same, okay. So that is why this randomness, okay, and when you calculate the error, when you showing the error bar in this randomness, okay, so they are not two equals, right. They are not two equals, okay. Because here I use some random number to each points, here I also use some random number, okay, while I showing the error bars, but these two randoms are different numbers. So they are all random numbers, right. So you see my points, or is still unclear? Yeah, any question? Okay, so if not, then we will move forward. So yeah, so next I do some visualizations, okay. Next to see which variable contribute most to your total error, okay. You can plot the error components, okay. So again I use the same exercise. So this is some examples, the kinetic energy problem, okay. So this is my kinetic energy and I derivative with respect to m and then I multiplied with a sigma m, right, and this is square. So this is basically my component of m and other one similarly for the other variable component of v, okay. So now I plot this, okay. So if you plot this, you see, so your velocity is to contribute to this error, okay, large contributions to the error, okay. So this point is clear or not? So if you just look into this formula, okay. So what is this formula? So your derivative with respect to the variables and times the sigma, right. So I calculate these two things, okay. One is the derivative with respect to my first variable times sigma and then square, okay. And the second component, so is basically sum over I. So my second component is derivative with respect to second variable times sigma, right. So yeah, so I calculate the component v is derivative with respect to second variables times the sigma of this variable sigma v and then square, okay. We have a two component and I calculate the pie chart, okay. showing the pie chart, you see the velocity contributions is much larger than the mass contributions, right? Because the velocity contributions have a large sigma v. Okay. So, if you see your sigma v is 0.2. Okay. So, I calculate at lab values. Okay. So, remember. So, I calculated lab values. So, that is why my lab values are sigma v since is large and sigma is small. Okay. So, that is why I have a large contributions from the velocity as expected, right? Because I have a large uncertainty. Yeah, any question? So, next I will discuss correlations. Okay. So, previously when I define the propagations of error propagations, okay, I think if you remember correctly. So, yeah, here. So, I already told that this is the uncorrelated thing. So, now I discuss the correlated one. Okay. So, this is the formula when the variables x1 and x2, the input variables are not correlated. Okay. Now, I will discuss when these variables are correlated. Okay. So, if the variables are correlated, let us say if you measure what is the physical means the correlations, if you measure let us say the length and width of a metal plate, okay, as it heat up. Okay. So, when the metal plate heat up and if you measure the length and width, so both measurements will increase together, okay, then the errors are correlated. Okay. So, you cannot say that okay, so I individually measure length and width and I calculate the error, okay, the summing up, okay, previously the way you calculate, okay, but this is not the correct, because when you heat up they basically related, okay. So, therefore, their error are also correlated, okay. So, you cannot ignore this, okay, the correlations. So, in that case you can define the generalized error propagations, okay, is basically again sigma f. So, I use capital F again. So, this is basically with respect to x derivative, partial derivative times sigma x square, and then with respect to y and sigma y square, just like before. Now, we have some extra term, okay. So, that is basically 2 times delta f delta x and delta f delta y times sigma x y. So, this is your correlation, okay, sigma x y. Previously, this term is 0, okay. There is a no correlations error, but here there is a correlations error. Okay. So, this is basically your covariance, okay, this sigma x y. Okay. So, in Mathematica we represented this thing in a matrix form. Okay. So, it is basically I have a matrix, I define a matrix that is my symmetric matrix. So, you see this is a symmetric matrix. Okay. So, this is xi equals to, so first element sigma x square. So, this one now I have a square, and the second one is sigma y and then square, and third one the off diagonal elements. So, these are the diagonal elements, okay, these things, okay, and the correlations are always appears as the off diagonal elements. Okay. So, the off diagonal elements, if you see the off diagonal elements is basically 2 lambda x y, right, but there is a 2 diagonal off diagonal elements. So, I put lambda x y each. Okay. So, it is basically lambda x y and lambda y x, and they are symmetric. So, that is why lambda x y equals to lambda y x. Okay. So, you can also write lambda x y, okay, because they are symmetric. Okay. So, this is the way once you define this. So, now how to calculate this sigma f? Now, we basically calculate the Jacobian. So, this is basically I define the Jacobian. So, the derivative with respect to variables. Okay. So, this is again a matrix times this covariant matrix. So, this is basically my covariance matrix and times the transpose of Jacobians. Okay. So, this is required for the matrix multiplications, right. So, let us say J sigma, okay, and then again J transpose. Okay. How do you multiply in a matrix? Okay. So, all these things are 2 cross 2 matrix. Okay. So, let us say this is my variables x and y, and I use again same functions. is a product of two variables x and y, and I define my covariance matrix is basically 0.1, 0.05, okay, sigma x y the correlations, okay, and again 0.05. So, these are the symmetric. So, I put same value and then again sigma y my 0.2, okay, and I calculate. So, I first assign this, I calculate the Jacobians. So, here the variables x and y. So, you calculate. So, this is a matrix. Okay. How to know this is a matrix? Just check. So, this is basically y x, okay, it is a column matrix. Sorry, it is a row matrix. Okay. So, it is a y x. So, now how to multiply? So, y x and then because your functions is x y, okay, that is why. So, when you derivative with respect to x, so this gives y, and when you derivative with respect to the second variable y, it gives x. Okay. So, that is why it is a y x, and times the covariance matrix. So, this is your covariance matrix times the transpose of this. So, then this is a column matrix. Okay. This transpose of this, this is a column matrix. So, if you multiply this, you see. So, this is basically this. Okay. So, you are 0.2 x square. So, you see the delta f delta x is basically the derivative with respect to x. So, it's y, right, and sigma x is 0.1, right. So, you see that 0.1 times y square, the first one. Right, because you see that sigma x square is basically 0.1. Okay. So, sigma x and square is 0.1. So, that is why you are not squaring again. Okay. And the second one is basically sigma y square. So, sigma y square is basically your 0.2. Okay. So, you see I define sigma y square here, okay, in the matrix. So, this is basically your 0.2. So, that is why 0.2 times x. Okay. So, 0.2 times x square. Okay. So, now the third one, 2 times delta f delta x. So, what is your delta f delta x? Is basically y, okay, and delta f delta y is basically x. So, 2 times your sigma x y. Sigma x y what is 0.05. So, 2 times 0.05 means that 0.1 times x y, right. So, see how easily we calculate this thing. Okay. So, you can calculate this using this matrix from. Okay. Yes, clear. You can use any functions here. You just put the functions and the variables, and you will calculate this. So, if you use 3 variables, then your correlation matrix will be 3 cos 3. Okay. So, this is used to estimate the variance of a multivariate functions, okay, based on the uncertainties of the input variables. So, in this case my input variables are x, y, and we know the uncertainties of this by this covariance matrix. Okay. So, this is user given. So, once you know these 3 values, these 3 things, you can calculate the variance of these functions, okay, f. Okay. So, by using this. So, this is the propagated variance, that means the variance of these multivariate functions. Okay. So, you can also use the around object again. So, what is that? So, the around object can also handle the correlations, but it requires to define the multivariate distributions or use the vector around command. So, if you use a correlations with the in the around objects. Okay. So, if previously when I call the around, so we see that there is a no correlations. Okay. So, now suppose your m and v are correlated. Okay. So, if there is a correlations, then we cannot use around. So, we use a vector around. Okay. So, you see your mean values, let us say 10 and 5. Okay. You have 2 variables and your mean values are for first variable is 10 and the second variable is 5, and we can assign the values with correlations, or the covariant matrix is basically vector around mean values and the covariance matrix. So, that means we assign the the mean values of first variable 10 and 5 with the correlations is basically your covariance matrix, this one. Okay. So, I already assigned the covariance matrix here. So, I use these correlations here. Now, I calculate the area. So, this is basically values with covariance the first one and the values with covariance in the second component. So, you can see the calculate the areas is basically again in the covariance form. Okay. So, you can just quickly check what is this. So, this is basically your first element in the matrix. So, you see. So, this is a 2 cross 2 matrix. So, this is basically your first column, and again if we just choose the second one, so you see. So, this is your first one, your only mean values 10 and 5, and the second one is the covariance matrix, right. So, once you calculate this, we just multiply it with this. Okay. So, if you multiply this, so 10 times 0.1 is 1, right, and 5 times 0.5 is 0.25, right. So, I think I have to so okay, let me split my screen again. Yeah, so so this is the way you can assign the, so the way you can assign the correlation matrix using the vector around functions. Okay. So, we just multiply it with this. Okay. So, 10.5 times this. Okay. So, this is the correlations. Okay. I use here. So, this is your covariance matrix. Okay. So, I use here. So, you see. Okay. So, if we calculate the area, we just multiply it with these two values. Okay. It's the mean times with error. Okay. So, you can visualize these things. Okay. So, once you visualize, you just check this. So, how to visualize this? You can plot the confidence ellipse. So, I plot the ellipse. Okay. So, my confidence level 0.95. So, this is basically 95% confidence level. Okay. And I plot this, the mean values and the covariance matrix, right. So, my mean values are 10 and 5, and the covariance matrix are already given here. So, this is my covariance matrix. So, we plot this. So, you see. So, your mean, the measurement of x. So, this is your 10. You see that the 10 here. Let us zoom this. So, this is your 10, and measurement of y. So, this is 5. So, this is the mean, and then but we have a error. So, error are basically your 1, 0.1, 0.05 and 0.2. So, that is why. So, your x axis have a small error, but y axis have a large error, right, because this is 0.2. Okay. So, your sigma y square is basically 0.2. So, that is why in the y axis, so there is a large deviations, okay, and in the x axis there is a small. Okay. So, that is why this is. So, in this way your confidence ellipse. Okay. Yeah, this is clear or not? So, this is the graphical view of the errors. Okay. Yeah, so far any questions, then I will come to the more interesting things. Okay. Okay, so let us discuss. So, instead of using this calculus or the derivatives, okay, or the around object, okay, so I can write an object. Okay. So, this is the around object or the vector around. Okay, I use to calculate the errors, right, basically formatting the errors, right. So, here I use around object, okay. And when I when I use correlations, I use vector around object, right. But you can also use some random data. Okay. So, Monte Carlo simulations. Okay. So, what is this? So, we perform an experiment, let us say 10 to the power 5 times, to see how the distributions of the result f x y behaves. Okay. So, let us first quit this thing. So, this quit means that I already remove all the variables if I assign, okay, somewhere. Okay. So, I quit all these things. So, I define a functions. So, my functions are basically x y. Okay. Now, I generate samples. Okay. The samples is basically I have a 10 to the power 5 data points, okay, and I choose a random variables. Okay. So, this is f, the 5 functions, okay, okay, where the x and y are the random variables. Okay. So, random variate I consider this normal distributions, Gaussian distributions, okay, with a mean 0.5 and 0.01. Okay. So, my first variables are generated from these distributions, my second variable, right. So, are generated from these distributions. Okay. I think I already discussed, okay, what are these distributions, okay, and also I discussed the PDF for this. Okay. So, these two, from these two distributions, okay, I assign some x and y, okay, randomly. Okay, this is my variables. Okay, and the functions is basically x times y. Okay, and I generate 10 to the power 5 time data points. Okay. So, this is my samples. Okay. So, I make a table. I am not printing these tables. This is a large table. Okay, large samples. So, I calculate mean, standard deviations, and histograms. Okay. So, if you calculate this, so you see. So, this is your mean, it is 6.19. From the plot you also see that. So, this is your 6.2, right, and 6.19, this is actually the mean. Okay. And you can calculate the standard deviations, and this is the histograms, okay, the last one. So, I performing a 50 bin. So, you also increase the bin size, let us say 100. Okay. So, you can do that thing. Sorry. So, this is the bin size. Okay. Number of bins, total number of bins. Okay. So, now if our functions is highly non-linear, so here the functions is basically x y, it is just a product. Okay. Let us say I consider functions e to the power x over y. Okay. So, then the standard error formula might be slightly wrong, okay, because the around object use a linear approximations, but your functions is non-linear, right. So, if we calculate the error using around functions, okay. So, I already told that the around functions is basically use some linear some first order Taylor series expansions. Okay. So, that is linear, right, the first order expansion. But if you do a Monte Carlo simulations, right, so then there is no first order Taylor series expansion, you can do properly, okay, with a Monte Carlo handle the curve error as well, right, perfectly, and it is exact. Okay. So, how to do that? So, first we again we define this histogram. So, this is my histogram. So, I define this is a hist variable. You see. So, this is the PDF from the so here what is the plot. So, you see the first one is the histograms, okay. So, the red one, okay, and the blue one is basically I plot it from the sample. Okay. So, this is my PDF, okay. It is a Gaussian, okay, and the first variable is basically the normal distribution is a Gaussian, okay, and the first variable is mean. I know how to define a norm this. So, this is a mean and this is standard deviation. So, I calculate the mean from the sample, I already calculated. So, this is my mean. So, I just use this and the standard deviations, okay, of the samples. Okay. So, remember I use samples. So, that is why I use the standard deviations that is embedded in the Mathematica. Okay. that use n minus 1 in the denominator. Okay. And I generate a Gaussian, this is a normal distribution Gaussian plots, and I plot using this PDF. Okay. So, you only plot these blue lines and you see that exactly match. Okay. Right. So, this is just for cross checking that. So, this is your actually so this mean and standard deviations calculated from these samples, okay, is exactly reproduce those things, okay, those PDFs. Okay. So, now we calculate the error. Okay. So, this is my error, right. So, this is basically 0 0 and so this is basically mean, okay, and the error, right, covariance matrix. So, if you see, so this is when I use vector around, right. So, this is the mean values and the covariance matrix, right. So, I use two variables, right. So, with the mean 0 0 mean values and with the covariance matrix is a 2 cross 2 matrix, right, and this is a multi normal distributions I assign to this term. So, I am not using vector around here. Okay. Okay, and then I randomly generate this with 1000 points. Okay. So, this is the random. Oh no, there wait. Okay, just a minute. Yeah, so let me share my screen again. Yeah, so you see, so I generated 1000 points from this with these correlations with a mean 0 0. So, you see, let us zoom this. You see that 0 0 is the mean and I generate the points with these correlations, okay, 1 0.8. If we change the correlation, let us say change the correlation 0.7. Okay. So, then you plot randomly. So, you see your correlation is changes. Okay. So, that is why this also changes. Okay. So, the generation point, if you see the changes, okay, 0.8, 0.8. So, you see the changes. Okay. It becomes clear in a moment. Okay. So, so this is the way I generate the random numbers, okay, with these correlations with this mean. Okay. So, you see that the mean is always 0 0 from these points. Okay. So, now I calculate so now I calculate. So, this is the ellipsoid, okay, as I already discussed here. So, how do you calculate this this ellipse, okay, 95% ellipse. So, this mean values and the covariance matrix. Okay. So, again I use the these functions ellipsoid and this is the my mean values 0 0 and the covariance matrix, okay, and I plot these two things in a one plot. Okay. So, this scatter plot, so the first one is the list plot and then comma the other one, okay, the region plot. Okay. So, you see, so this is the thing. So, the 95% points are within this circle. Okay. So, this is your 95% probability regions, okay, within that circles. Now, we can also calculate the covariance eigenvalues and eigenvectors of this matrix. Okay. So, if you calculate this, so you just use eigen system of this covariance matrix, because I use the matrix here this. Okay. So, that is why I assign to this covariance matrix and I calculate this eigenvalues and eigenvectors. So, what are the eigenvalues and eigenvectors? The eigenvalues are basically the directions, the ellipse point, and the eigenvalues are how long the ellipse is in those directions. Okay. So, it is basically the length of arrow is the eigenvalues and the eigenvectors are basically arrows. Okay. I will show. So, let us say I have x is 1. So, this is my eigenvalues times vectors square root of this, okay, and x is 2 is basically 2 of square root of eigenvalues times eigenvectors. Okay. So, now if you plot this, so you see, so in these directions, okay, so you have a large eigenvalues, okay, and in this arrow, so there is a small eigenvalue. So, there are two eigenvalues. Okay. So, the length of arrows, okay, is basically represent the eigenvalues, okay, and the directions are the basically eigenvectors. Okay. So, that is why your ellipse is in this way. So, the your major axis and minor axis. So, major axis is large because in this way the eigenvalues is also large, okay, and the minor axis is small, that is why the ellipse is this. So, this is basically your 95% confidence level ellipse, okay, with the arrows. Okay. So, the major axis of ellipse, so this is the directions of the maximum variance in these directions. Okay. So, it represents the primary trend in the data. So, data is already trend in these directions, okay, because all the points are generated, you see, if you see the points. So, all the points are generated along this diagonal, okay, and the minor axis, the short arrow, okay, this one, the perpendicular one. So, this is the directions of minimum variance. So, in these directions the variance is minimum. So, that is why the data is not generated. Okay. Okay. So, this is also you can use this vector around. If you do a vector around, so you just calculate these two things, okay, just like around. So, in around you only calculated the error of a particular point, there is no correlations, but in the vector around, if you do a vector around functions just like as before. So, you just point these two things. Okay. So, from this point you see that the variance in the x axis is large and the variance in the y axis is small. So, that is why you see the variance in the x axis is large and variance in the y axis is small. Okay. But if you do a proper pictures, you have to do a Monte Carlo simulation. Sorry. That is the best way, because you know the actual non-linear things are appears there, but they just use a linear approximation. So, and they plotted these things. So, you can actually when you are talking about error, so you have to plot this ellipse, okay, 95% probability ellipse. Okay. So, you can also manipulate these things. So, in the previous discussions, in the previous class I will show what is the manipulations mean. Manipulation means that we can manipulate everything, the correlations. Okay. So, here I make a slider for correlations. Okay. So, if you do this thing, so you see, so my correlations is 0.8 just like as before. Now, if we change the correlations, let us say 0.72 changes, so we change the opposite way, let us say change the negative correlations. Okay. So, you see, so the negative correlation means the opposite way, the ellipse is the opposite way. Okay. So, your correlations is now minus 0.8 okay, almost. Okay. So, in this way you can check change the correlations and see, okay, how your trends in data. Okay. So, if you choose a correlation, let us say 0. So, you see it is almost circle. So, there is no correlations, right. So, now if positive correlations, that means there is a trends in data with this diagonals. Okay. If you change the correlations, that means your slope is changes actually. Okay. Or if you go to the negative directions, that means this basically in the opposite diagonals. Okay. So, in this way you can just manipulate, okay, and your correlation matrix will be -1 to +1. Okay. If we reach 1, then there are some singulars. Yeah. So, I will discuss those in the next class in details, but yeah, so just for use. Now, if you calculate, we solve some problems and then I will stop today. So, let us say I have in a resonance tube experiments to measure the speed of a sound, okay, and a student collected the following set of measurements in meter per second. Okay. So, I have to measure the speed of a sound, and I have this set of data set. Okay. And due to the nature of equipment, the several measurements were repeated multiple times. Okay. So, I measure 338 meter per second the speed of a sound 8 times. Okay. So, this is my frequency multiple times, how many times I measure. So, I measure 340 12 times, I measure 341 25 times, I measure 343 35 times, I measure 344 10 times, and I measure 346 10 times. So, which of the following is a good estimate including the error bar, okay, for this bit, okay, based on this experimental data. So, first I assign the values. So, this is my values 388, 340 this, and these are the frequencies, right. So, I assign the frequencies corresponding. So, then so my data is basically, so I have to assign 388 times, okay. So, I have a total, how many total data set? So, you can just check this. So, your total, yeah, 100 data, right. So, I have 100 data, but 388 is 8 times. So, I make a data set is basically, you can use these functions constant array and then values and frequency, okay. So, that actually helps you to build the full data set, okay. So, in these full data sets you have a 388 times, 340 12 times, you can see, you just yeah, you just see. So, this is a map thread. So, that is why it is not showing, but it is already there, right. Yeah. So, in this map thread, so you can no, I think something is problem. Why there is a 2? So, just so, this is my values and this is frequencies. So, I assign this, yes. So, I have 100 data, right, and then I calculate the mean values just using this mean data and the standard deviations and the error of the standard deviation. So, this is error bar, okay. You can also use around. So, this is around. So, the arguments of the mean values and the sigmas, right. So, this is your the standard errors, right. So, once you assign this, so you basically the results are finally this. So, this is a similar problems in the assignment. So, you just calculate in this way. Okay. So, remember if in the problem, so there is a one confusion here, the standard deviation. So, when you calculate, we use n or n bar, right. So, if you use n in the problems, because if you calculate theoretically, so there is a no experiments, okay. So, then if you use n, okay. So, then big crucials if you use standard deviations, I mean you should not use standard deviations in whatever is in defined in the Mathematica, right. You should multiply it with yeah. So, basically length of data minus 1, right, and then square root right, and then divided by square root of n, right, square root of data. So, you should multiply it with this. So, it changes slightly. Yeah, in this case it is not affected, okay, because you have a large number of data sets. So, it is not problem, okay, up to this decimal place. So, they are rounding off, okay. So, since that after decimal points you have a 2 numbers. So, that is why your error is also in 2 numbers. Okay. So, this curve fittings, I have a little time to go through this, but okay. So, let us do one exercise and yeah. So, let us do one problem. So, generate a table of n random numbers using random reals, okay, functions, and note that these numbers are centered at 0 and calculate the standard deviations of these n numbers and repeat this process while n running from 100 to 2000 in step of 200 and feed the results to this from and calculate the what is the values of b from the feed. So, first I clear all my a, b and n. So, I generate the random number. So, this is my data set. Yeah, it is basically -1 to 1, right. So, I calculate so I generate the number random real number -1 to 1 with 100 to 2000 in a step of 200, right. So, 100 to 20,000, so no, 2000. So, 100 to 2000 in a step of 200 and I generate this. So, I assign n and the standard deviations of this. And next I feed the nonlinear. So, this is basically the standard deviations of this n numbers. So, I use these functions. If you again if you use the standard deviations manually, then you have to multiply it square root of n minus 1 over square root of n. So, big crucial here. So, but I use for simplifications I use the standard deviation that is already defined in the Mathematica, and now I use these functions nonlinear model fit. So, that is my data, because your data is basically the standard deviations of these numbers. So, that is why I calculate the standard deviations of these numbers. So, numbers are the real number within -1 to 1 where n is goes to 100 to 2000 in a step of 200, and I feed this. So, this is my data and this is my functions. Feeding functions is a into the power b. So, I just put here a into the power b. What are the variables a, b and at the n, right. So, these are the variables and this is the functions. Sorry, n is the functions, these two are the parameters. And it is also variables, but yeah. So, these are the parameter variables and this is the functions. I mean f of n. So, better we can say that this a and b are the parameters and n is the variable. And I use nonlinear model fit to fit the models. So, once you fit this, you can calculate the best fit parameter, just put NLM. So, this is your model parameter fit, you just put this NLM in best fit parameters and then print the parameter table and NLM parameter table. So, what is this? So, this is print the parameter table, when this just print the parameter table, and once you call this NLM, because NLM is basically your nonlinear fit. So, that gives you a parameter table. So, this is the parameter table. So, here you see the best fit parameter is the first one, the values of a and b. So, this is the values of a is 0.5 to these values and b is 0.15 this, with the error is basically this for the a and this is the error for the b, and this is some t statistics and this is the p value. I will discuss in the next class, since we do not have time. So, in the next class I will discuss what is t statistics and p values, and also the more details on the curve fitting and the parameter estimations. So, this is similar problem to the assignment, that is why I just solved this, that helps you to solve your assignment problems. So, let us first quickly go through this. What is this? So, this t statistics, so t statistics is basically your estimated values of a standard error, right. So, estimated value, that means that you measure, right, and the standard error is basically the noise kind of things. So, this is basically signal to noise ratio. So, high t statistics suggests that the effect is real, that means your signal is greater than your noise. So, that means if the t statistics is value is high, that means your effect is real, and if your measurement is correct. So, and the p value, and the other one is the p value. So, that represent the probability that you will see your result if the two parameter value was actually 0. So, this is some null hypothesis testing, and a small p value means that your parameter is statistically significant. So, if you now see, so this p value is small, I mean less than is 0.05 is fine. So, here you see the p value for this parameter a is very small, 10 to the power minus 8, and for this case this is also small, less than 0.05. So, it is fine. Okay. So, that means these two parameters, the p value since is small. So, your fit is correct. Okay. And also the t statistics, you see that there are high values, so it is already order of 10. Okay. If you increase more and then if you get more values. Okay. So, means that if your data is correct, so then your data is measured, if you measure precisely, then your t value is also large. Okay. So, I can also, yeah, so let us say this one. Okay. So, I generate a pseudo data, so that is 2.5 and my g is 9.8, actual g is also 9.8. Okay, and I assign this and I generate some random data with these corrections. Okay. V0 plus GT, this is my object, falling object equations. Okay. And I choose a random number that is very small, minus 1 to 1, where yeah, so this is my data table. So, where t goes to 0 to 5 with a step of 0.5. Okay. So, these are the discrete data set. Okay. You know how many data sets, right. So, 0.5 steps is basically 10 data sets, right, 10 points are there. So, if you do a linear fit, because this is a linear function. Okay. So, that is why I use a linear fit model. Okay. So, linear model fits and data, and my variables are, this one is constant, okay, and this is g times t. So, this is basically 1 and t with the coefficient is basically t, right. So, you will see. So, this is the your parameter. So, that best fit parameters written v naught and g, the coefficient of these two. Okay. And in this case, you see that t statistics for the t parameters is very large. Okay, because yeah, so this is basically g, right, and you see that this is 9.8 and actually g is 9.876. So, that is why the t statistics is very large, because your predicted value and this one is very close. So, okay, so I think I should stop here. If you have any questions. So, you can always use nonlinear fit even if you fit the linear functions. So, the nonlinear fits is very good. I mean, you can use always nonlinear fits, okay, even you fit the things. Okay. So, you see that the nonlinear fits arguments and the linear fit arguments are different. So, in case of when you use linear fits, if you use 1 and t, so here the variable is t, but if you have to use the coefficient of this. So, the first one is basically 1, because there is no variable, and the second case the variable is t. So, that is why I put t, and I assign my t is the variables on, I have to fit this. So, that is why, but in nonlinear case, we first assign a data and then functions and the variables a and the parameters a and b and the variable a. So, you see here the a and b I assign the parameters, but here I assign this v naught and g, I am not assigning v naught and g. So, rather I assign 1 and t, right, because this is my v naught times 1 and this is g times t. Okay. Because this is a linear function, so you can assign this way. Okay, so I think it is clear, right? Any question? In the next day, I will discuss this on more details. Okay, the curve fittings and the parameter estimations. But for solving assignment problems, I think this is fine. Okay, since there is no more questions, I will stop here. So, I will upload this on the YouTube. You can also revisit and see if you have any questions, you can ask in the next class. Okay. So, then see you. Bye bye.